Hi, everyone. We're going to continue to look at these medical testing statistics, going to continue to explore this mammogram example. I want to introduce you to a little bit of important vocabulary, but also look at some of the consequences of that vocabulary, because it turns out that the same test, this mammogram test, can mean very different things in different situations. That's what we want to understand now. Let me just bring up the screen. There we go. Where is it? There we go. So we're looking at medical testing vocabulary and some of the consequences of this vocabulary. So to pick up where we left off, we have this grid. And remember, the patient, the doctor, doesn't know which row somebody is in. They only know whether they tested positive or tested negative. So they know whether they're one of these 5,000 or so women or one of these 94,000 women. And the vocabulary we've used so far, the prevalence is the percentage of people in the population who have the disease, the percentage of people getting tested. The true positive rate is the percentage of people who have the disease who test positive, hopefully most of them. And the true negative rate is a percentage of people who do not have the disease, that's this row, who correctly test negative. So that's our basic vocabulary. I should say the true positive rate is often called the sensitivity, how sensitive the test is to the disease, how often does it pick it up. You can think of the sensitivity of a fire alarm being how minor of a fire does there have to be for the fire alarm to go off. Whereas the true negative rate is sometimes called the specificity. How specific is this test? Does it only catch people who really have the disease, or does it accidentally catch some people who don't? So sensitivity and specificity are other terms for the true positive and the true negative rate. To be honest with you, I have a hard time keeping these two words straight. They sound too similar to one another in my brain. So I tend to use true positive and true negative, but you will see both of them. Okay? So again, the person being tested does not know whether they have the disease or not. If they did, they wouldn't take the test. They only know which of these two columns they're in. They know which of these two groups they've landed in. So how should they interpret that result? I'm repeating a calculation we did at the very end of the last video. Of the 5,680 people who tested positive, what percentage of them have breast cancer? That's called the positive predictive value. If you have a positive result, how predictive is that of having the disease? And you would calculate that by taking the true positives, the 720 people with breast cancer who tested positive, and dividing by all of the positives, number 1 over number 2. And if you do that, you get 0.123 or 12.3%. Only 12.3% of women who test positive on a routine mammogram actually have breast cancer. That is a startlingly low number for what seemed like a pretty accurate test. On the other hand, when we look at people who test negative, a lot of women tested negative, and you might say, hey, those positive results, most of the women who tested positive were just fine. Does that mean that I should be worried about a negative result? Does that mean a bunch of women who test negative actually have cancer? Well, to find the negative predictive value, how likely are you to be fine if you test negative, you would take the number of women who have no breast cancer and tested negative and divide by all the people who tested negative. So it'll be 3 here over 4. And if you do that, you get 0.999. 99.9% of women who tested negative are actually just fine. So a positive mammogram, you're still fairly unlikely to have breast cancer. Positive mammogram, probably fine. Negative mammogram, almost a guarantee that you are healthy. It is perhaps surprising that the positive predicted value and the negative predicted value are so different. Why is that? I mean, remember, the true positive rate is 90%. The true negative rate is 95%. So those are pretty similar. Given that, why is a negative test result almost always correct, where a positive test result probably wrong? Think about this for a little bit and give me whatever thoughts you've got on the form. Okay, welcome back. Turns out this is all about the prevalence of the disease in our testing population. Remember, only 8 women out of 1,000 who get mammograms, that was 800 out of our 100,000, actually have breast cancer. That means 992 women in 1,000 do not. And some of those are going to test positive by error. You get some false positives. So that means that even a very low false positive rate, a small number of false positives among these 992 women, is still going to be a lot of false positives compared to the true positives from these 8 women. So this very low prevalence, this overwhelmingly number of people who are healthy, means a low false positive rate will still make for more false positives than true positives. Let's look at some pictures because this can be a little hard to understand. Here's a grid. Oops, I've got to move my face again. Here's a grid of, I think this is 400 people. It's 20 by 20 dots. And if we're looking at about 0.8% of the population having breast cancer, this would be these 3 red dots up here. So let's just imagine that they all test positive. Let's ignore the false negatives. So out of these 400 people, we're going to get 3 true positives. But we're also going to get, with a 5%, with a 95% true negative rate, so a 5% false positive rate, we're also going to get these 20 false positives down here, because all of these healthy black circles, about 5% of them are going to falsely test positive. So you see that we have many more false positives than true positives, even though only 5% of the healthy people accidentally tested positive. Okay, what if we tested a different group? What if we tested a group of people where 5% of them had breast cancer instead of 0.8%? So what if we tested a higher prevalence population? Now these red people are going to have breast cancer. I actually messed up. 1 or 2 of these should be people who would actually have breast cancer but wouldn't test positive. So then 1 or 2 of these would be false negatives. You can imagine slashes through 2 of these. But let's say our test is perfect and catches all the cases of breast cancer. So we would have these 20 true positives, and we would still have a 5% false positive rate among the black healthy people. So these red outlines down here, these are going to be false positives. So now the same test, the same 5% false positive rate, but now with this different population, now we see that about half of the people who tested positive really are positive. So that tells us this positive predictive value, this what should you believe if you get a positive result, doesn't just depend on the test itself, it depends on who's being tested, on the rate of the disease in the testing population. Let's carry out the calculations to see how this works. Calculations that correspond to the picture I just showed you. So we have this higher risk group where 50 in 1,000 women, or 5% of them, have breast cancer. Same test, same true positive rate, same true negative rate. So I've done the calculations for you here. Out of your 100,000 women, we now have 5,000 who have breast cancer instead of the 800 who did last time. You can push that over to find out how many of them test positive and negative. Out of our 95,000 women who do not have breast cancer, you will find that 5% of them test, 5% of them test negative and 95% test positive. You can add up going down to find out the number who test positive out of my 100,000 and the number who test negative. So looking at this data, I would like you to calculate the positive predictive value. If you test positive, what's the chance you're sick? And the negative predictive value. If you test negative, what's the chance that you're healthy? And enter those into the form. Okay, here are my calculations. The positive predictive value is 4,500 divided by 9,250, and that's 49%. So that means almost half, because that's right about 50%. Almost half of the people who get that scary phone call actually have breast cancer. That's much higher than the 12.3% we saw below. The negative predictive value is a tiny bit smaller, but only a tiny bit. It's this 90,250 divided by this 90,750, and that will be 99.44%. So that means that only over 99% of the all clear letters of the everything look fine really are healthy. So this test has a much higher positive predictive value and a slightly smaller negative predictive value than our previous example. And it's the same test. It's the same mammogram. What's changed is who we're testing. So why don't we only test this high-risk group? I mean, for the high-risk group, the positive test was much more likely to be true. We weren't scaring as many people unreasonably. So why do we test lower-risk populations instead of focusing on high-risk groups? Think about that for a moment and answer on the form. There's this issue of trade-offs. If we test the high-risk group, our tests are going to be a lot more believable, but we're going to miss some cases. There are some low-risk people who actually have cancer. Not a lot of them, but a few. So if we only test the high-risk population, we're going to miss them. So we have to decide what's the right population to test. This has been a real discussion in mammograms. At what age should you start routinely getting mammograms? Should you start at age 40? Should you start at age 50? And by routine, I mean if you have no family history, no other risk factors. And that's exactly a question of how high is the prevalence? And as the prevalence in the population goes up, it becomes more convincing to believe that we should test everybody. It seems like we should just test everyone. I mean, you want to catch cases of cancer, but remember that testing and false positives are difficult. Testing is stressful. The false positives are stressful. They're expensive for the patient as well as for the system. And so you have to decide when is the prevalence high enough that it's worth these large numbers of false positives to catch the occasional true positive? And this involves both thinking about the rates of false positives and in some cases also figuring out, well, if we catch the disease early, does that actually help us save lives? These questions are difficult. We're going to look at some information about pap smears rather than mammography and this idea of trade-offs on our next video.